Thank you, everybody, for coming out to our talk. We're going to be talking about Graph and our usage of Graph in working with Airline to see how we can incorporate a Graph database along with their reservation and routing system. Just by way of introduction, my name is Jason Plurad. I'm an open source software developer and advocate. I work with the Apache TinkerPop project and the JanusGraph project. Chin Wong, he'll be speaking later in the session. He's also on the open source team, and he focuses more on JanusGraph and performance and contributes to other open source projects as well. So we're talking about airports. We're both from the United States, and it was interesting to see how we both got here. I was joking with somebody earlier today that we probably jinxed ourselves by having this use case, because we both ended up being delayed severely on the way here. Chin's flight on Sunday actually got canceled, so he ended up traveling a day later. My flight was okay, but then I got delayed in Amsterdam, and I missed my connection, so I was actually stuck there for an additional 14 hours, which was amazing coming from the East Coast. So you can see there are several stops you can take, and it doesn't even cover the breadth of the different airports that we could have potentially traveled through. I mean, we both took a eastward journey, but we easily could have gone in the other direction if that made sense. So let's wind it back a bit. So graph as a data structure really is not new. The theory of graph in mathematics goes back all the way to the 1700s with Leonhard Euler, who worked on the bridges of Königsberg problem. And what he was trying to do was understand how to traverse from the different land masses in Königsberg across the 7 bridges. And what he was realizing was it wasn't necessarily the way that to traverse each bridge without repeating and visit each landmass. The most important part was the connections and being able to traverse each bridge and do it in such a way that you touched each one. This laid down with your land masses. You had your vertices. This is your land masses in this scenario, and the bridges represent the connections. In graph theory, we call those the edges. So in a mathematical graph, that geographical map turns into this. When we started looking into open source graph technology, our initial use case was mostly around social analytics. This was around the time when Facebook and Twitter were starting to really gain steam. And the idea of understanding how people collaborate together was really of interest to us. What we did as one of our first projects in the graph space is we took all of the data that we were generating internally in our company through a tool called IBM Connections. This is a social tool where you can have discussion forums, file sharing, and those types of activities. And we wanted to understand better how people across our company were collaborating, because we knew, I mean, basically that everybody in the company needed to work better together. For example, when we started talking about graph, we started asking around in different parts of the country and different parts of the business, who else is doing graph, and all of a sudden, all these different hands come up. So obviously, we have in our company of 400,000 people a few inefficiencies in terms of navigating through the employees to understand who are the leaders, who are the influencers. And being able to pull those together into a social graph made a lot of sense in terms of understanding how to give the proper incentives to those people who connect those different communities and raise the bar for everybody. And what we found, once we started talking throughout the company about graph, we started finding more and more use cases beyond the social graph, which really got us started. Master data management, this is one that actually came up today in Mandy Chesel's keynote, the idea of being able to understand how your data, where it's coming from, what it means, how it connects together. The Apache Atlas project actually uses a property graph under the covers to store some of its data. And I guess we're seeing graph more and more in the mainstream media today also. Just understanding, like with the Panama Papers, understanding how different organizations are involved. And the United States, obviously, what's going on with Trump and the investigations going there. It's all about how data is connected, and the graph itself lends itself to that. So what we'll be talking about today is the data structure called a property graph. So with a property graph, you have vertices and edges, and on those vertices and edges, you can have properties. So taking our initial example of how Chin and I both arrived here in Berlin, you can see I'm along here on the bottom. I started in the Raleigh airport, went through Detroit to Amsterdam to Berlin. So on the vertex node, we have several properties. It typically has a label, which kind of tells you what type of node it is. In a social graph, you might have people. In this kind of graph, we have airports. You have a name, an identifier, the code, and other properties that would make sense. For the edges, you can also put properties on here as well. So here we have like the specific flight number, how long it was, and the arrival and departure times. So what we like, I think when developers first come to the idea of a property graph, it makes a lot of sense. It's considered a very whiteboard-friendly type of model. As you can see, it's easy just to draw it up on a board and get a good understanding of how things connect together. And even though today we're mostly talking about just an airport graph, as you start to bring together diverse sets of data, as I said, with people, you have, and other types of entities that you might want to pull in the graph, all you have to do is create another vertex node and make another connection, and you can instantly add it to the graph. So as a NoSQL type of engine, it makes it very friendly to expand your data model. When we first started on this mission, we did a survey of open source, and we looked through about a dozen different graph databases. And what we found interesting was the majority of them implemented this standard layer, or de facto standard layer, called TinkerPop. And what TinkerPop does is it provides a common structure API and a query API for graphs. So the structure API, again, defines your vertexes, your edges, your properties. And then you have this graph language called Gremlin, which gives you the ability to pull your data back out. So Gremlin itself, it's a functional data flow language. It provides you the right constructs to be able to navigate through the graph. It breaks down mostly into 3 types of steps. You have a map step, which allows you to transform the object you're looking into another one. You have the filter, so it allows you to remove elements as you navigate through. And the idea of a side effect, which allows you to do some computation. So what we're looking at here, just to give you a flavor of what the Gremlin language looks like, is the shortest path algorithm. This is a very common type of algorithm that you would do on a graph data structure. And the key point here is really the idea that it makes it easy to do this type of construct where you have a repeating traversal. If you were to do this in a relational type of system, you would typically end up having to do multiple joins, recursive joins. And with Gremlin, it's relatively simple in terms of how it lays out. So I'll walk you pretty briefly through this. So here we start through the graph vertices. We'll start with the Raleigh one. What we're going to do is we're going to repeat here. We're going to repeat going out on the route edge. So we have the edge label is called route, and we're going to do a simple path. What that'll do is that'll prevent us from doing a cycle. So if I started in Raleigh and I go to New York, I wouldn't want to come back to Raleigh to find another way to get to Berlin. That doesn't make any sense. And so this is our breakout clause. This is going to get us out of that loop until we reach the TXL airport. Key thing we have here is the ability to limit. So you want to limit your results. One of the first things that people typically run into when you have this kind of graph algorithm is that you could end up exploring the entire graph. If I followed every single airport, every airport has 100 different ways out of it, you could end up in various different places very quickly. So you could end up with an exponential type of growth on your path. So being able to limit it is important. So then we want to see the path by code. So this will tell us which nodes we visited on our way to Berlin, and we could see the results here. There are plenty of ways to get there in one jump. Not all of them necessarily make sense. So this is a very simple algorithm. What you would typically do in your own program would be to add additional logic to filter out things that might not make sense. So here, for example, me going from Raleigh to Los Angeles to Berlin doesn't make sense because I'd be going 3,000 miles in the wrong direction before going to Berlin. So TinkerPop itself is just a graph abstraction. It provides, as I said, the structure and the query. But to build a real solution, you need a graph database. And this is where JanusGraph comes in. JanusGraph it's a fork of a project called TitanDB, which had gone dormant. So we got together with partners such as Hortonworks and Google to establish the JanusGraph project at the Linux Foundation last year. And what JanusGraph provides to you is a vendor-neutral open source community with plenty of partners who are trying to build a scalable graph database. And we'll talk a little bit more about how that comes into play. Some of the key features here is the ability to scale horizontally. There are plenty of graph databases out there now that implement the TinkerPop layer. But not many of them are open source, and that's pretty much a big differentiator for JanusGraph for companies who are interested in doing an open source kind of development. So you can see the founders listed, and since we launched at the beginning of last year, lots of companies have joined on, such as Netflix and Uber, and we have plenty that are in production. It's Apache licensed as well, so it carries on the spirit of an Apache project, even though it's at the Linux Foundation. This is an architecture diagram of JanusGraph. So at the top would be your graph application. These light green boxes, these are your TinkerPop layers. So being able to have the TinkerPop API, JanusGraph is a full implementation of the TinkerPop stack, both on the OLTP side. These are your neighborhood type of traversals where you're zoning in on a specific vertex and branching out from there, and the OLAP implementation. This allows you to do more full graph type of operations. The parts in dark green here, these are the specific parts that JanusGraph provides around transactions, defining your schema, and being able to define the storage format. Under the covers, JanusGraph itself is able to utilize different scalable databases as the ultimate storage. When the creators of the project originally started, they didn't want to reinvent this layer. They wanted to build on top of existing technologies such as Apache HBase and Apache Cassandra. They both implement the big table style of storage. So beyond these, there are plenty of other storage backends that are able to work with JanusGraph. So there's ScyllaDB, which is an implementation of the Cassandra APIs. There's another one called Yugabyte, which again implements the Cassandra APIs. But it could work with other types of storage as well. I think there was another database called ForestDB that I heard recently is now living down here. And Google Cloud Bigtable, it's an implementation of HBase. So plenty of opportunities here, depending on your deployment of how you want to run JanusGraph. We have here the external indexing backends. So what this allows you to do is to take advantage of these distributed indexing backends to do full text search, geographical search, numerical range queries. So it makes for an interesting configuration. that you're able to do a little bit of everything with Graph. One other item I'll add here is that typically what we found in deployments of Graph is that it's never just Graph. You usually have a little flavor of a NoSQL backend, even a relational backend, and you have a mix of indexing. It's selecting Graph specifically for your navigational graph, where you're looking more specifically at how items are related, where the graph comes into play. So coming up next, Chin will take us through some work that we've done, more specifically on the Airline use case and how we use it to evaluate performance.
So today I'll focus on a performance experiment we did with JanusGraph, and then I'll talk about the reservation use case, in particular how we did it and the lessons we learned. Okay, the first thing I want to go over is our environment. Right, we chose to run our performance test on this physical servers because we want to eliminate any possible overhead, if we use containers or VMs. As you can see, we have pretty powerful machines, up to like 56 logical cores and so on, with disk, RAID 5 SSD. Because we want to see how much we can push through, right, as far as the transaction per second. Okay, for read and write. We're running our tests on Ubuntu, and we use a number of public tools. These are sort of common tools you use for monitoring and also profiling Java applications. Right. For instance, JMeter, we use it to drive the REST requests. Nmon, we use it to gather the system performance numbers. Visual VM helps us to look into the Java insights, and GC Easy helps us to look at the garbage collection details, and we have Grafana as our dashboard. But that's not enough because we're dealing with graph database, right? The first challenge we see is we don't have a lot of existing data for us to play with. And also we want to try our test cases with different volumes. How we can get that? So we decided to create our own tool, right? So with that data generator, you can specify how many, we call it vertex types or vertex labels and also edge labels, and then how many records for each of them. You can specify the relationship. You can have, we call it super node. That means you have many more relationships for certain nodes. Right? You can generate that data to simulate your real data before you even commit to any kind of graph databases. So that's the first tool we created. And the second one is how do we look into the schema? What kind of data types, what kind of properties, what kind of indexes you have? We don't see any existing good tools. So we decided to write our own. Okay, so you can easily specify your definition for your schema in a JSON file. And then we just quickly created the new schema for you. Or you can even update if you already have a schema in place. Lastly here, we often see data stored already in CSV files because that's the most common way to export data from existing relational databases. We're talking about big data. You have millions to billions of records. How you move them quickly into a graph database? All right. So again, we create a batch importer. We fully utilize your system resources with multi-threading and so on. So we can push the data quickly into our database. All these tools are open source. You can go to the link and check it out and also contribute. Okay. So here, before I go to the results, is our topology. On top is the load driver. We have a Java driver on the left-hand side for the insert and update. We have the REST request using the Gremlin queries, going through JanusGraph, and then at the bottom we have a cluster of 3 physical nodes. We run one database system at a time. These are all open source NoSQL databases, right? Solr, Cassandra, and HBase. Okay. So our goal is to first find how many records we can push through into this database. The second thing is we want to compare 3 different quite popular NoSQL DBs. Okay, the first test case we have here is to insert vertices. In JanusGraph, that means insert only. We don't need to do any search. Okay, so write operations, basically. We push 40 million records into the system as fast as we can. Okay, we achieved 272K per second, with Solr. And as you can see on the chart, we also achieved more than 80% of CPU usage for the DB servers on average. Okay, compared to others, you can see Cassandra and HBase, they are much lower in TPS and also lower in CPU usage. The next case is insert edges. In JanusGraph, that means we need to find the target vertex first and then update it with the edges. Okay, so in the database terminology is actually search and update. Okay, so with this combination, again, the TPS is on the chart. We got 132K for SolrDB. So that's actually 2 operations, right? Although we call it 1 TPS, that means query and update. As you can see, it's much better than the other 2 in our test case. The third one is the graph traversal. In this case, we want to make it a bit more realistic, because you can always query for record by the ID. That's really fast. But this time, we want to search for instance, all the your followers that retweeted one of your tweets, right? So it's actually 3 steps traversal. So you have to find your follower and then their retweets and if they retweeted your tweet. Okay. Anyway, in this case, on the left side is the TPS again. At 100 concurrent users, all of them are fairly close. But once we increase the load to 1,000 concurrent users, you can see the red one is for HBase. It started to show saturation. Okay, even we increase more load, it doesn't increase the TPS much. As far as for Cassandra, it slowed down in terms of the performance gains. Right now, you can see Solr is the best performer, even for the query case. Okay, on the left side, it shows the response time or latency. So this helps you to evaluate how much resources or what kind of configuration you need if you have certain SLAs. For instance, if you want to have sub-second response time, and your expected concurrent user is 100. So any of these 3 databases would do, right, on this chart here. Oops, sorry. Here, okay. But if you want to support 1,000 concurrent users, my suggestion is gonna be using Scylla because it will give you this, sub-second response time. Okay. As far as the additional lessons we learned from this experiment is for each database, they require different kind of configuration and operations. For Cassandra, we found the cluster node it's a little bit hard to bootstrap. Okay, it requires certain kind of timing, to be correct. We also found it used a little bit smaller memory, so it might be good for smaller servers. For HBase, the biggest thing we have to work with to make sure that the load is balanced between the cluster nodes. Okay, otherwise we have hot region that will degrade the performance a lot. For Scylla, we found it's very easy to do the clustering. It's well self-tuned because they use this active memory management, right? Even without a lot of load, it's trying to actively manage the cache. That also made the CPU usage not representing the real load. Even with very low workload, CPU usage very high. But the good thing is they have a nice dashboard. You can actually see the true performance numbers. And also, it's using the Cassandra API, so we don't have to configure anything differently for Scylla. Okay, so that's our sort of pure performance study. Now we go back to this customer use case. They want to find any sort of routes from point A to point B at any given date and time. And they provide like 1 year worth of data, okay? Of course, here we say 1 stop, 2 stop. You can do as many as you want. The data volume is not that huge, as you can see. We have 600 something airports and some flight schedules. But each schedule can represent a day, a week, several weeks to several months of flights, okay? They can say this is good for a whole year too, okay? So during the traversal, we need to consider additional conditions or requirements, from the business side. For instance, from point A to point B, what's the maximum mileage you can travel? Or what's the maximum stopover time you can have, right? So we have to apply additional logic to solve that kind of issues. What we learned from this exercise is actually JanusGraph gives you additional ways to do this kind of calculation. They have this groovy extension. If you found something is hard or impossible to do in Gremlin query, you can always write your own functions to handle that, okay? But let's go through this list quickly. The first lesson we learned is we have to look into the performance side before you decide what's the data model for your use case. Because only you know your use cases well, okay? One thing we also found is the read and write workloads usually are sort of in the opposite side of the performance, right? If you have very good read, maybe you don't have as good write, right? So knowing that ratio for your use case is important. And also when you query, what kind of levels you want to go to traverse through your data, right? Once you know all that, you need to start consider options. Do you want to normalize your data or even use redundant data to make your query faster? Of course, JanusGraph provides a number of indexes you can use to help the search results. I mentioned a little bit, try to use different approaches to get the results back. Gremlin query is only one of them, right? You can do some pre-process. You can, like I said earlier, write extension using Groovy. But one key I want to mention is in graph traversal, the most expensive thing is you have too many options going out early. And eventually you found a lot of routes are not really valid, okay? That's the most expensive operation. So if you can, try to filter out as early as possible. So in our case, for instance, the maximum mileage is X. Then you want to start tracking that from the first route and next route. Once it exceeds that, then you stop, right? In order to do that, actually in Gremlin query, there's a methodology called stack, I believe, right? You can start tracking that as a global variable, okay? So once you are done with your modeling and your programming, the next thing is to know your systems, right? JanusGraph is very flexible and dynamic. You can use different backend systems. So you need to understand that and fine-tune that. With JanusGraph itself, it has a number of things you can adjust for performance. One of them is a thread pool and the size of the JVM heap size. Okay, you don't want to have a too small, and you may get the out of memory exception. Too large will make your GC very slow and long. And if possible, always think about multi-threading, multiple processes, and also look for some sort of cloud and auto scaling if you don't want to deal with this kind of performance issues on your own. As you can see, there are so many things you can tune and turn the knobs to make the system perform better. Just be patient, right? Enjoy the journey. So that's all I have today. Jason, do you want to come up and we can probably answer some questions?
Should go to the next slide.
I think that's the end. Okay. Go ahead.
Thank you for the presentation. It was really interesting. I have a question about queries in JanusGraph. Does it support streaming results? Like it's like very well patterned when you have a lot of queries and you'd like to get the result as fast as possible to get back to the user. For example, I found like first row in just a few milliseconds. I'd like to return it back to user, but users can wait for a couple of more seconds to get like updated results. So is it possible to do with JanusGraph?
The results are streamed. You have the capability of doing it, but I think you would need to evaluate how reasonable that is. I mean, because depending on the query, based on how the traversal is evaluated, you still could be waiting a long time. But streaming is a capability that's provided by TinkerPop. You get back an iterator, so it's up to the backend. So depending on which database you're using with TinkerPop, it will stream the results to you.
Okay.
Do any tests in virtual environments? So you did your hardware, did you try anything in virtual environments?
We did run this on virtual environments. In fact, we didn't see a whole lot of differences. Yeah. But still, we want to use, bare metal to make sure that's the best we can get. Go ahead, please.
My question is about performance. If you can go to the slide 16 with the graph. On the left-hand side, you can see that if you have 100 or 1,000 users or requests,
Sure.
then the performance is better and better. Why? So it means that for 100, the overhead is so high that it's not so good to use it? Or?
Because once we have more requests, we can parallelly process all of them then the average is faster. That's how we calculate it. Because we have a driver sending in a fixed amount of requests. Once we have more drivers, like 1,000, we send in more. So that means the system at 100 is not in full throttle. Okay? Yeah. But at the 1,000, as you can see here, right? For HBase, definitely we cannot drive it more. In fact, for Solr, we can probably put additional 200. Then it will reach a point, it will never go higher. Okay. Any questions? Well, if not, Jason, I think, thank you very much for coming.
Yep, thank you.